It's on there now? It looks like it is. Okay. Okay, so back to where we were in chapter 14. So plan for this week is going to be this, guys. Today, we did all the stuff with the test and what's going on, but we're just going to start grinding through chapter, or keep grinding through 14 tomorrow. And if you had been in my class any other year other than this year, would have been a normal block day. What we'll do is we're going to go about an hour, maybe a little bit more, continuing in chapter 14. And then I'm going to stop. We're going to pre-lab a lab we're going to do on Thursday. And then I'm going to give you guys some work time, just because listening to me is only going to do that so long. And so, remember on Thursday, you have that rainbow, that color lab is due on Thursday. So I'm going to give you some time to work on that. On Thursday, we'll probably do 15, 20 minutes continuing in chapter 14, and then we're going to do the lab. So that's kind of the way this week looks. So here's the problems. I've already went over this. We talked about these things. We talked about properties of acids and bases. We said acids are mainly found in the refrigerator or in the food pantry, and bases are found as a cleaning product, like in the laundry room. And then this is where we left off. So I was kind of rushing at the end. So let's pick up here. So what we said was definitions. So now definitions of acids and bases. And we said there's two definitions. The and you never need to name them. You're not going to have to name them. But the Arrhenius definition and the Bronsted-Lowry of an acid are the same. So the definition of an acid is the same, is that they give up H+. So the definition of an acid, they give up H+. To be an acid, the compound has to have H. And there's actually a third definition, which is not going to be in our class, and I might just barely touch on it 1 minute, one day next week. But for us, is that acids give up an H. So to be an acid, it's got to start with an H. But bases have two definitions. And the one that you guys first learned when you first started chemistry was the one my chemistry students still know, and this is the one that they're going to know, because they're not going to have time to get to the second one, is that they give off OH ions. And when you first were learning chemistry in the fall of first year chem, you learned bases is giving up OH. So NaOH, KOH, all those were bases. But there's a second definition of bases, and it's just right here. They're a proton or an H+ acceptor. So there's one definition of acids. Acids give up an H, but there's two definitions of a base. One is that they give off OH, and the second one is they are a proton or an H+ acceptor. Okay, and I think I went over this. Didn't I go over this? No, I think I had talked about this. And if you look at this, this is an example here. And I'm going to talk about this, but here to this morning, and I'll talk about it more. But the acid and base are on the left side of the arrow. And on the right side, they call them a conjugate. A conjugate. It's kind of like a partner or a sibling. And the acid always has a conjugate base. So this would be the conjugate base. The acid has a conjugate base, and they differ by a single H. And the base has a conjugate acid. So the acid has a conjugate base, and the base has a conjugate acid. But for right now, what you look at is the flow of the hydrogen. So if you compare the reactant side, the left side, to the product side, the right side, note that HCl becomes Cl negative. It has lost an H, so by definition, it is an acid. And carbonate, CO3 negative 2, has gained an H, so by definition, it is a base. So acids, one definition is they give up an H. Bases, two definitions, either they give up OH or they accept an H. Okay, so here is another example of a reaction that's an acid-base reaction. Again, if you look at the left and look at the right and look at it in terms of what happens in terms of the H's. So HCl and H2O, and on the right side we have Cl. So this must be the acid. This has got to be the acid because it has lost an H. It's lost an H. And the H2O has become H3O. It's gained an H. So by definition, then water must be a base. And some things like water, you'll see, and there's other things that we'll look at as we go through this chapter. They're called amphiphilic. I'll define that. But they can act as an acid or a base. It really depends on what they combine with. Note too, when something loses an H, not only does it lose an H, but its charge decreases by 1. Its charge decreases by 1. So HCl becomes Cl negative. Its charge decreases by 1. And then if something gains an H, its charge increases by 1. Okay, so, and that's one thing we'll actually do a lot of in this chapter is we will write a lot of equations. Okay, so kind of key thing today here are strong and weak acids and strong and weak bases. Jokes, Liza, jokes. I almost forgot. Need to do jokes here. Let's see if I got any in here. What do you get, or how do you feel? How do you feel if you cross a sheepdog with a melon? Melancholy. Thank you, Lord. What do you get if you cross 2 young dogs with a pair of headphones? Hush puppies. I'm liking my jokes. Oh, I got more. What do you get if you cross a hunting dog with a telephone? A golden receiver. Wait, I have more. I have more. What lies at the bottom of Bass Lake? Bass turds. On the bottom of Bass Lake would be bass turds. You may not have known this, but are potato, it's a question. Are potatoes good at sports? No, they are just good spectators. Okay, the last one. Kylie, you may not have known. Are you from California? You may not have known this. I don't know if anybody's from California. They do not celebrate Christmas in California. Did you know that? They do not celebrate Christmas in California. You know why? They couldn't find 3 wise men and a virgin. They like that one. That was a good one. Also, in Passograph, this is that sulfur penny lab, and I actually just put this. I just put this in Infinite Campus. So this grade is in Campus too. Okay, so a strong acid, and there's a short list here, which you guys are going to have to commit to memory. A couple things, which are going to be the strong acids and the strong bases. But strong acids completely ionize in water. I'm actually going to do a quick little demo today to show that to you. But notice here, there's just an arrow going to the right. And so what happens with a strong acid or a strong base, what you start with goes completely to the right. So what you start with is really just ions. Like today, I'm going to use the same, for this little demo I'm going to do, the same acid, the 6 molar hydrochloric acid that we use in the lab. And really, it's not HCl that's in the solution, but it's H plus ions and Cl negative ions. It's a good electrolyte. Again, I will demonstrate that today. And it produces a lot of ions. And here's a short list you got to remember. Here are the strong acids. Okay, this is how I always remember this. Okay, no, it's got to have H in it. And 3 of these come right from the halogen group, the purple group up there. That is HCl, HBr, and HI. Now, you could go, how about HF? Well, HF is this really unusual acid. One day I need to show you, I have a video of this guy who does this experiment with hydrofluoric acid. But hydrofluoric acid is a strong, weak acid, but it's not a strong acid. So again, how I remember it. So we got HCl, HBr, HI, 3 halogens. And then HNO3, which we have used in labs, nitric acid. Sulfuric acid, which again, we have used in labs. And the one that's really the outlier is actually the strongest of all the acids. It's called perchloric acid, HClO4. So again, those you're going to have to remember. All the other acids are weak acids. Those are the 6 strong acids. So again, the 3 halogens, HCl, HBr, HI. Nitric acid, which we've used a lot in a year and 3 quarters of chemistry. Sulfuric acid, which again we used a lot. And the one that is the least familiar is the strongest of all, perchloric acid. Weak acids are all the other acids, so hundreds of other acids. And they ionize only a little bit. And so what happens here, you can see, so notice a double arrow. So it goes to the right, but then it comes back to the left. And notice the diagram. On the strong acid, you have a whole bunch of ions. And you're going to see here in a moment, the light bulb apparatus that I've used before is going to get very bright in a strong acid, a strong base. But in a weak acid, weak base, there's very few ions. The K is a small number. The K is the same K that we used in chapter 13, so that means there's very few products. There's a lot of reactions. It's a weak electrolyte, so it's not going to turn the light bulb on very well at all. All other acids are weak. Okay, so let me put up, so strong bases are going to be, again, it's going to be another list. I'm going to give you another list to memorize here. But it's really going to be the same thing. So while you guys are writing this down, let me demo this real quick. A strong base, like a strong acid, is going to dissociate completely in water. So it's going to break it completely down. So it's going to turn the light bulb on very good. It's a good electrolyte. In reviewing what we learned back in the fall, we call these strong electrolytes. And strong electrolytes, when we have those in an equation, we're going to work on writing equations in this chapter, are going to dissociate completely. And there was three categories. There were the strong acids, which we just talked about. There were the strong bases, which is on the overhead now. And there were the soluble salts. So it was ionic compounds that had one of four ions, Na, K, NH4, or NO3. And those can dissociate completely. Okay, so let me, while you guys are writing this down, so I'm just going to show you, and again, I've had this device out other times this year and last year too. It's this little light bulb apparatus with these two electrodes. And if I put a screwdriver across the electrodes, the light bulb lights up. We talked about that. Why? Because the circuit is completed. Well, if I take just some distilled water, okay, and I test this, I'm expecting nothing to happen because there's nothing in there to conduct electricity at all. Well, now I'm just going to add just a squirt of that acid that we used last week. So this was 6 molar hydrochloric acid, a strong acid. Well, now I put this in there and it lights up. Well, over here, Jordan and Lori could tell you, as I put the screwdriver across, they can see what's completing the circuit. But in there, in here, and even they're way smarter than me, but I don't see anything. What's in there, though, what has happened is this, and you'll see as we go into this chapter, is that actually strong acid, strong base problems are a little bit easier. So what happens is the HCl dissociates. And when we do ice problems with these, we almost won't need to. So with the HCl, if there's a lot of HCl, here we have 0, 0. Well, what happens is when we put it in water, it completely goes away. And so what we have in there, what I'm trying to say, and we'll do this with numbers as we go through this chapter, but what happens is all the HCl is converted into ions. And so what we can't see in there is those ions, which are moving around, which carry electricity. Well, now I'm going to do a weak acid. So you can see what?
Around the palms, you can see the.
You can see it. Yeah, right. You can see the business. Okay, again, distilled water. And now I'm going to put in, I have got so acetic acid. There it is. Okay, so I'm going to put some acetic acid. This is kind of the most commonly used example that chemistry teachers use for a weak acid. It's not very concentrated, but if I put it in there now, boy, it barely lights up. Did you see it, Jordan? I'll have a little bit more. I could see it maybe barely lighting up. Lights up a little bit. Okay. So, but notice it doesn't light up nearly as much. Okay, so what is going on there? This is acetic acid. So it breaks down like this. Well, here again, if I do an ice table, again, if I have a lot and 0, 0, well, here it's just a little. So almost all is left. That's what happens. Where here we get just a little and a little, which means there's not very many ions in there to conduct the electricity, and that's why the light bulb doesn't light up very much. That's what happens. Okay, and if I do the same with bases, I'm going to get the same effect. So here, here's just distilled water, nothing. And I'm going to put in here some sodium hydroxide, which is a strong base. And one thing I'm going to talk about here in a second, I'll talk about it right now. So I gave you the list of strong acids. Here are the list of strong bases. And again, this you're going to have to put in your brain. For being a strong base, it's supposed to line up there. It's really bad. Okay, so here's the list of strong bases. So the strong bases, okay, the strong acids, HCl, HBr, HI, HNO3, H2SO4, and then HClO4. The strong bases combined with OH, just like it says here, the alkali metal hydroxides. That's any of these right here in the pink column with hydroxide. So I just did NaOH. So NaO or LiOH, NaOH, KOH, any of these with OH. And this is, and I'm going to show you how I do it. The alkali earth hydroxides are also strong. And that, and what I always tell students is any of the alkali metal hydroxides with, and this is the element that I've lost, I can't find, calcium. So calcium, so CaOH2, SrOH2, BaOH2. So that's the list of strong bases. Okay, so any of the alkali metals with hydroxide, as well as CaOH2, SrOH2, BaOH2. The other one that I don't think comes up in any problems is technically the strongest of all bases is NH2 negative. It's called amide. The amide ion is the strongest base of all. So that's the list of strong bases. Okay, now a weak base is going to be just like a weak acid. This is not a great example. It didn't work that well. But we'll try this. Is ammonia is kind of the best example of a weak base. Acetic acid, a weak acid. It doesn't turn on. I just have some just ammonia that you guys can find at Walmart, Target. I'll put just a little bit in there. Sometimes it does a little better than anything. There you go. Okay. So you get the idea. It's the difference between a strong acid and base and a weak acid and base. And what you're going to see as we go through this chapter when we do calculations is that the problems that are weak acid, weak base problems, they are the ones that are the most complicated. So a weak acid, they ionize just very little. That's why the light bulb didn't get very bright. A weak electrolyte, and a lot of them have hot nitrogen because they have that non-bonded pair. Okay, so here's that concept of the conjugates that I was talking about. Okay, so what is in here, what is down here is what's up here. So if you're taking notes, and again, what you do on these problems is you follow the H's. Again, if you compare the left side to the right side, and always on the product side, on the right side, you have the conjugates. Those are kind of, like I said, like the partners. So if you look at what happened here, and you look at the H's, when there's a single H difference, it's got the conjugate. So this is acetic acid, and over here is acetate ion. It differs by a single H. So the acid has a conjugate base. The acid has a conjugate base, and the base has a conjugate acid. So the acid has a conjugate base, differs by a single H, And the base has a conjugate acid, or conjugate acid, yes. It has a single H. And again, note what happens here too, a little detail. When something loses an H, so going C2H3O2 to C2H3O2 negative, the charge decreases by 1. So when something loses an H, its charge decreases by 1. And water here gains an H. So this is a base, this is its conjugate acid. So when something gains an H, its charge increases by 1. So this is an acid-base pair. So an acid has a conjugate base, and a base has a conjugate acid. The acid-base pairs differ by a single H. Okay, and then here's kind of a point we're going to get to more as we go. But which base is stronger? There are two bases. There's water, and there's the acetate ion. And I'm going to get to this tomorrow, definitely. And we'll, as we go through this chapter. Did you have a question, John? But this is what we're going to say. This is new, or even if you were following your chemistry teacher last year, Mr. Conyers, Mr. Hodis, and I did not get to this. But the conjugate base, and I'll say this again. I'll say it a couple times now, but I'll say this again as we go through this chapter. But the conjugate base of a weak acid, that's what this is. The conjugate base of a weak acid is a stronger base than water. The conjugate base of a weak acid is a stronger base than water. The conjugate base of a weak acid is a stronger base than water. So then we can say, and we will say this, so the conjugate base of a strong acid is a weaker base than water. So the conjugate base of a weak acid, or I'm sorry, the conjugate base of a strong acid is a weaker base than water. So weak acids produce stronger bases. So the question here, which is a stronger base? So we've got water and we've got acetate. The answer here is acetate. And again, this is something we'll talk about more as we go through this chapter. Okay, if Kc is a smaller number, which base is stronger? That's what I was just saying. So the conjugate base of a weak acid is a stronger base than water. And one thing as we get deeper into this chapter, one thing that's going to be important in this chapter is going to be to write out equations, chemical equations, and we'll actually spend time just on writing equations. But we'll have acids and bases, and technically the only time that we will have to write water as this actually is a mistake down here. This should be H3O positive. I'll say that again. This should be that. I should have corrected that. I said I was going to correct that in period 2, and I never did. But I'll say it again. So we're going to have strong acids, weak acids, strong bases, weak bases. The only time where you really have to write water as a reactant is when you have a weak base, because you have to have a source of H. Now for acids like here, and like I've been doing all day, I've written water as a reactant, and that's fine to do. For acids, it really doesn't matter. But for a strong base like NaOH or KOH, you don't include water. If you include water, it's going to mess you up. And I'll talk more about that. But technically, the only time you really have to write water in the equation is when it's a weak base. And with acids, be it strong or weak, you can write water or not. Sure.
I think the reason why you put it H plus and Cl negative is because right above it says often H3O plus.
Right here. Right. And that's an important thing. And you're probably right. But just to be correct, the way we learned it in chapter 13, if I wrote H3O, I really should have there. But the point Jordan's making, if I first of all, if I go here, and then I'll come to that. But this is just showing the same thing. So the acid and the base, so this is an acid is going to lose an H. So the conjugate base, so right here would be Cl negative. Cl negative. And then the base has a conjugate acid, so this would be H3O positive. H3O positive. So the same concept. So again, the conjugate means a pair. So the acid has a conjugate base, Cl negative. And the base has a conjugate acid, H3O positive. So here, which is stronger? Okay, so this is a conjugate base of a strong acid. So the conjugate base of a strong acid is weaker than water. So the answer here would have been water. This is something we're going to get into tomorrow. We'll talk about a lot tomorrow. And this is the point Jordan was making. When you see H3O, H plus, those are equivalent. Those mean the same thing. H3O is called hydronium. And the big topic in this chapter is something that we would have spent in first year chem a couple days on, is pH. And it's really an easy calculator thing. But pH is about the concentration of the H plus. So really, these are interchangeable. And Jordan, you're exactly right. I think when I did that, that's why I did that. So H3O and H plus are interchangeable. So if we write the equilibrium constant, so here we go back to what we were doing back in chapter 13. So the products on the top, and again, like Jordan pointed out, those are equivalent, but really I should have said that as H3O positive times Cl negative. So the products on the top and HCl on the bottom. Why didn't I not write in water? Right? It's a liquid. Remember, liquids and solids, we said were one. So this is the Ka. The Ka, it means the same thing, but the A means it's an acid. So, okay, well, this is a good place to stop. This is where we're going to pick up tomorrow.
See you tomorrow, Mr. Wood.
Okay, Tyler, you bet. See you guys. Good job.
No. Something entirely different.
See, so how did the Thunder Ridge game go?
We lost double overtime.
Oh,
yeah.
man.
I watched that. You played for 9.
Do you have the Prince interview? I'm a little behind. I need to order it. Do you have to have one?
I do. You just want to take a picture
Yeah,
of
just
it?
take a picture. Just so I can get it right. Thank you. And then, you know what the ID or whatever I could look for? Did you get there like a specific?
You know, the one thing that I did is I just went to Amazon. I looked up, I just said AP chemistry. Get the one, just like the picture. There's one that's got 7 tests. I think, well, this is.
Oh, thank you.
See you, Mike.